Hello students, welcome to my virtual class. In today's class, we will discuss solution, that is unit 2. Under this chapter, today's lesson is vapor pressure of solutions and Raoult's law. Students, you know gaseous state of a substance that exists either as liquid or as a solid at normal pressure is called vapor. Okay. The process by which a liquid changes to vapor is called evaporation or vaporization. Okay. At constant temperature, the pressure exerted by the vapor in equilibrium with its liquid is called vapor pressure of the liquid. Let us consider a situation in which a closed container is partially filled with a liquid. Okay. Liquid starts evaporating and the vapor formed occupies the empty space above the liquid. Vapor molecules, due to their weak forces of attraction, are in random motion and colliding with one another and with the walls of the container. Okay. The vapor molecules with lower kinetic energy cannot get rid of the intermolecular forces of attraction exerted by the molecule at the liquid surface, thereby return to the liquid phase. This process is called condensation. Both evaporation and condensation are taking place simultaneously. Okay. At the initial stage, the rate of evaporation is greater than the rate of condensation. Okay. But with the time, as more number of vapor molecules accumulate in the space above the liquid, the rate of condensation increases. Therefore, a state is reached when the rate of evaporation becomes exactly equal to the rate of condensation. Okay. And a dynamic equilibrium is established between the liquid and its vapor. That is, at this state, the amount of liquid and the vapor remains constant with time. That is, the rate of vaporization and rate of condensation is same. Okay. The vapor in equilibrium with the liquid is called saturated vapor. Here it is saturated vapor. Okay. And the pressure exerted by the vapor on the walls of the container is called saturated vapor pressure or simply vapor pressure. Okay. So the definition is here: at constant temperature, the pressure exerted by the vapor in equilibrium with its liquid is called vapor pressure of the liquid. Okay. At particular temperature, the vapor pressure of a pure liquid is always constant. Okay. So now we see factors affecting vapor pressure of a liquid. Under what factors? What are the factors affecting the vapor pressure of a liquid? First of all, it is nature of the liquid. At constant temperature, the vapor pressure of any liquid depends on its tendency to evaporate. Okay. A greater tendency to evaporate is higher is the vapor pressure of the liquid. For example, intermolecular forces of attraction of ethanol are weaker than that of water, indicating a greater tendency of ethanol molecules to undergo in the vapor phase. Therefore, ethanol has a higher vapor pressure than water at a particular given temperature. Okay. Secondly, we see temperature. Okay. An increase in temperature of the liquid increases its number of molecules with higher kinetic energy, and therefore the particle of its able to pass into the vapor phase by overcoming the intermolecular force of attraction. Okay. Therefore, at higher temperature, the vapor pressure will be higher. Okay. Next, we see the vapor pressure of a solution containing non-volatile. That is, non-volatile means it cannot vaporize. Okay. Non-volatile solid in liquid solvent. That is, if we make a solution with adding a non-volatile solid, that is non-volatile, for example, a non-volatile solid is glucose or sugar, okay, salt, these are non-volatile solid, and therefore the vapor pressure of a solution, that is solution with non-volatile solid, is always less than vapor pressure of the pure solvent. Okay. Let us see the reason of the lowering of the vapor pressure. The number of solvent molecules per unit surface area of the solution is fewer than that of pure solvent. Let us see a diagram. This is pure solvent and this is a solution containing non-volatile solid solute. Okay. Here the blue color balls are indicating the molecules of the pure solvent, and green color balls are indicating the non-volatile solute particles or molecules. At a given temperature, the vapor pressure of the solution containing non-volatile solute is always less than the vapor pressure of the pure solvent. Okay. The reason is that the surface of the solution containing solvent molecules along with solute molecules, whereas the surface of pure solvent consists only solvent molecules. Thus, the number of solvent molecules per unit surface area, okay, of the solution is fewer than the pure solvent. Here the number of solvent molecule is less than this much area. Okay. Now, since the solute particles are non-volatile, it cannot go into the gas phase. Therefore, only blue color particles, atoms, sorry, molecules will go into the vapor phase. Therefore, number of molecules that is able to go to the vapor phase is lower here, and here is higher. Therefore, pure solvent has higher vapor pressure than the solvent solution containing non-volatile solute. Okay, this is the reason. For example, if this is a water, pure water, and this is a solution of glucose. Okay. Now let us see the law regarding this lowering of vapor pressure given by scientist Roult. Okay. Roult's law of lowering of vapor pressure when the solute is non-volatile. Okay. At constant temperature, the vapor pressure of a solution containing a non-volatile solute is equal to the product of vapor pressure of its pure solvent at the same temperature and mole fraction of the solvent in the solution. Okay. That is, vapor pressure of a solution P equal to mole fraction of the solvent X1 into vapor pressure of its pure solvent, that is P naught. Hence, P equal to X1 into P naught, where P naught is the vapor pressure of the pure solvent at that temperature. X1 is the mole fraction, that is number of moles present, number of moles of the solvent molecules present in the solution. Okay. Divided by total number of the moles, so this mole fraction. P is the vapor pressure of the solution. By this formula, we can calculate the vapor pressure of a solution. Okay, if we know the mole fraction of the solute or solvent, okay, and vapor pressure of the pure solvent. Now we try to explain with a graph, that is graphical representation. Okay, along the x-axis here we plotted mole fraction of the solvent, that is x1, and along the y-axis it is vapor pressure of the solution, that is P. Okay. The equation P equal to x1 into P naught is like the equation of a straight line, that is y equal to mx type. Okay, therefore the graph is will be a straight line going through the origin. Okay, so we see when the mole fraction of solvent is 0, that is here no solvent molecule is present, and since the solute is non-volatile, therefore vapor pressure is 0. As we increasing the mole fraction of the solvent, that is volatile component, the vapor pressure of the solution increases slowly, and at this point when the mole fraction of the solvent is 1, that is all total component is water, no solute molecule is present, it is pure solvent is here, therefore it is the vapor pressure of the solution is equal to the vapor pressure of the pure solvent. On going along this direction, if we just increase the moles of the solute, then the moles of the mole fraction of the solution is decreasing, and therefore vapor pressure is decreasing. When there is no solvent, all are the solute, that is mole fraction of the solvent is 0, then vapor pressure is also 0. Okay, this is the Raoult's law of solution containing non-volatile solid solute. Okay, so I think you understood the formula and the statement. So now we go to the second law, that is Raoult's law when the solute is okay. Before going to that, we see when mole fraction is 1, that is pure solvent, P becomes P naught, that is vapor pressure of the solution becomes vapor pressure of the pure solvent. Okay, now we go to the other law, that is Raoult's law when both the solute and the solvent are volatile. Okay. At constant temperature, the partial vapor pressure of a volatile component of a solution is equal to the product of vapor pressure of the pure component at the same temperature and its mole fraction in the solution. It is almost same. Rather, I say it is same for the individual component as Raoult's law of non-volatile solute. Here, both the solute and solvent are volatile, so for both the components, Raoult's law is applicable. Okay. Suppose at a given temperature, the vapor pressure of pure solvent, pure component 1 and 2, we can say 1 for solvent and 2 for solute, okay, are P1 naught and P2 naught. Since both are volatile, both have vapor pressure in its pure form, okay, respectively, and their partial vapor pressure are P1 and P naught respectively, okay, in the solution. Then according to Raoult's law, we have partial vapor pressure of component 1, you may consider it as a solvent, that is P1 equal to x1 into P1 naught, just like previous equation. Okay. And partial vapor pressure of component 2 is P2 equal to x2 into P2 naught, or x2 is the mole fraction of the component 2, that is solute. Okay. Now, according to Dalton's law, we know that total pressure of a gaseous mixture is equal to the partial pressure of the components, sum of the partial pressures of the component, that is P, that is total vapor pressure of the solution equal to partial pressure of component 1 and plus partial pressure of component 2 in the solution, which in turn equal to x1 into P1 naught plus x2 into P2 naught. Here we are considering the binary solution, that is 2 component. If there are 3 component, then it will be P1 plus P2 plus P3. Okay. Let us explain the Raoult's law of volatile solute with an diagram. Here also we plot the mole fraction along the x-axis and vapor pressure along the y-axis. At this point, the mole fraction of the component 1 is 0 and mole fraction of the component 2 is 1. That is, it is pure component 2. Therefore, at this point, the pressure of the solution is equal to the vapor pressure of the pure component, that is P2 naught. As we move along this direction, the mole fraction of x2 is decreasing and mole fraction of x1 component 1 is increasing. Therefore, vapor pressure due to component 2 is decreasing. Okay, this green line, and vapor pressure of x1 due to component 1 is increasing. Okay, and the total sum of vapor pressure due to x2 and vapor pressure the component 2 and vapor pressure due to component 1 is denoting by this solid blue line. Okay. So, as we move in this direction, vapor pressure due to component 2 is constantly decreasing and vapor pressure due to component 1 is increasing. Okay. At this point, since mole fraction of component 1 is 1 and mole fraction of component 2 is 0, that is, here it is pure component 1. Therefore, the vapor pressure of the solution is P1 naught. Okay. And between this point to this point, these are the vapor pressure of the solution, that is, the value of any point in this solution is P equal to x1 into P1 naught plus x2 into P2 naught. For example, at this point, the x1 is value of x1 is here. If we put x1 here and x2 here, we get the pressure of the solution. Okay. Here we are considering that the pure vapor pressure of component 1 is greater than component 2. If you consider P2 greater than P1, then this side is will be up and this side may be down. It is the same result will be obtained. Okay. So now if x1 equal to 1, therefore x2 will be 0, then the vapor pressure of the solution, it becomes vapor pressure of the vapor pressure due to component 1, that is equal to x1 into P1 naught. Although x1 is x1 become 1, therefore the vapor pressure of the solution become vapor pressure of the pure solvent pure component 1. Okay. When x1 equal to 0 and x2 equal to 1, that is mole fraction of the component 2 is 1. That means component 1 is absent here. Therefore, vapor pressure of the solution is equal to x2 into P2 naught, where x2 equal to 1, that is P equal to P2 naught, that is vapor pressure equal to vapor pressure of the pure solvent. Okay. Now we see one numerical problem regarding on the Raoult's law. 18 gram of glucose is added to 178.2 gram of water. If the vapor pressure of water for this aqueous solution, what is the vapor pressure of water for this aqueous solution at 100 degrees C? Okay. So here the amount of solute, that is non-volatile solute is given, and the amount of solvent is also given. Okay. We have to calculate the vapor pressure of the solution, that is P, and temperature is given at 100 degrees C. Let us see how to solve this problem. We have to first calculate the mole fraction. Okay. To calculate the mole fraction of the solvent, we have to know the number of moles of solvent and solute. So here number of moles of water, that is N1, okay, is we know number of moles N1 equal to W1 by M1, where W1 is the weight of component 1, that is solvent, and M1 is the molecular mass of the solvent, that is component 1. Okay. This formula, this is the famous formula N equal to Wm, we all know. Okay. Here the W1, the weight of the solvent, that is water, equal to 178.2 gram in gram unit, and the molecular mass of water is 18. Therefore the number of moles of water in the solution becomes 9.9. Similarly, number of moles of the glucose, N2 equal to W2 by M2, where W2 is 18 and M2 molecular weight, molecular mass equal to of glucose equal to 180. Therefore the number of moles of glucose equal to 0.01. So mole fraction of the water in the solution X1 equal to, we know, N1 divided by N1 plus N2. N1 here is 9.9 and N1 plus N2. So we find the mole fraction of the water, that is solvent, equal to 0.99. Now according to Raoult's law, we have vapor pressure of the solution equal to mole fraction of the solvent X1 into vapor pressure of the pure solvent P1 naught. Okay. So P equal to X1 into P1 naught. X1 is 0.99 and P naught, that is vapor pressure of the pure solvent. We know at 100 degrees C the vapor pressure of pure water is 760 mmHg. That is, it is its boiling point. At boiling point, vapor pressure of any liquid is equal to the atmospheric pressure. Therefore at 100 degrees C vapor pressure of pure water is also atmospheric pressure, that is 760 mmHg. So we put the value of P naught here and we get 752.4. Therefore at 100 degrees C vapor pressure of the solution will be 752.4 mmHg. Okay, this is the answer. And now we see if it is pure water, then the vapor pressure will be 760 mmHg. Since a non-volatile solute is added to this water, the vapor pressure is lowered. Okay, it is lower than 760 mmHg. It is 752.4 mmHg. Okay, I think you understand the system or the problem, how to solve this kind of problem by Raoult's law. Okay. Next we see another problem of Raoult's law when both the solvent and solutes are solute is volatile. Okay. A solution of ethyl alcohol and propyl alcohol has a vapor pressure of 290 mmHg at 300 K. Okay. Here both the component ethyl alcohol and propyl alcohol are volatile. Okay. So vapor pressure of the solution is 290 mmHg at 300 K. The vapor pressure of pure propyl alcohol is 200 mmHg. If the mole fraction of ethyl alcohol is 0.6, what is the vapor pressure in mmHg if in pure state at the same temperature? Okay. So we have to calculate ethyl alcohol's vapor pressure, okay, at this temperature. So if mole fraction of ethyl alcohol, ethyl and propyl alcohol in solution are X1 and X2 respectively, and the vapor pressure of them in their respected pure state at 300 K are P1 naught and P2 naught respectively, then total vapor pressure of the solution according to Raoult's law, we see P equal to X1 into P1 naught plus X2 into P2 naught. Okay, this is the formula we get from Raoult's law. Here the given the mole fraction of isopropyl alcohol, mole fraction of the ethyl alcohol is 0.6. Therefore, mole fraction of the isopropyl alcohol X2 will be 1 minus X1. Okay, since we know X1 plus X2 is always equal to 1. 1 minus 0.6 equal to 0.4. P equal to 290, that is vapor pressure of the solution equal to 290, and P2 naught, that is pure vapor pressure of pure propyl alcohol is 200. Therefore, we if we put these values in this equation, we get P equal to 290 into X1 equal to 0.6 into P1 naught we don't know, plus X2 equal to 0.4 into P2 naught we know, given here is 200 mmHg. By solving this equation, we get P1 naught equal to 350 mmHg. That is vapor pressure of pure ethyl alcohol at 300 K is 350 mmHg. So, it is very easy to calculate the vapor pressure of any component, vapor pressure of the solution by Raoult's law very easily. Okay, I think you understand the problem easily. Okay, now at the end of today's class, we see the question answer session and the homework. Okay, state Raoult's law for a solution containing volatile component. These questions are frequently coming in CBSE and TBSE board exams. Okay, state Raoult's law in its general form in reference to a solution. General form means non-volatile solute. Okay. State and explain Raoult's law for a solution containing non-volatile component, TVSC. Okay. These questions are collected from the board exam paper, previous board exam papers. Okay. What do you mean by vapor pressure of a liquid? What are the factors that affect the vapor pressure of a liquid? Why is the vapor pressure of ethyl alcohol is more than that of water at the same temperature? At 80 degrees C, the vapor pressure of a pure liquid A is 520 mmHg and that of a pure liquid B is 1000 mmHg. If a solution of A and B boils at 80 degrees C under 1 atm pressure, what is the mole fraction of A in the solution? 1 atm equal to 760 mmHg is given. The answer of this problem is 0.5. Okay, you try to solve this problem by the Raoult's law of volatile solvent. Okay, so how you enjoy this class? Tell me, and if you have any queries, any problems, any clarification, you can you don't hesitate to call me on this number or WhatsApp me on this number. Okay, so for following my class, once again thank you to all of you.